I am the Assistant Portfolio Manager for the Prolonged Field Care Portfolio. We were previously called the Forward Surgical, En Route, and Critical Care Portfolio. So just a little bit of nomenclature change there for you. This is just all right. So what are we going to talk about here today? Our capability gap is hemorrhage detection. So as we know, 87% of preventable deaths on the battlefield occur prior to medical treatment facilities. And of these deaths, 24% were potentially survivable. Of that 24%, 91 were due to hemorrhage alone. So this includes junctional hemorrhage, truncal hemorrhage, and extremity hemorrhage. So what we're looking to do is to provide our medics with the capability to detect hemorrhage prior to the patient going into hemorrhagic shock. So as we can see here, of the 888 preventable deaths that were due to hemorrhage, about 67% were due to truncal hemorrhage, 19% due to junctional, and another 14% were due to extremity hemorrhaging. And this is also during the time period from 2001 to 2011. So we had fielded tourniquets, including junctional tourniquets at this time, but we can still see that we have some preventable deaths that are due to hemorrhage. So here we can see just a couple images that I pulled up for you today. So internal hemorrhage from blood trauma is not necessarily externally visible to the medic. So the medical provider, including at the point of injury, may not be aware of the extent of hemorrhage and the volume loss that each service member is undergoing if there's not a visible entry or exit wound. We can also see penetrating trauma may be more extensive than what is evidenced by entry and exit wounds, and this is also evident in low light situations. Many of our operations are taking place at night with low light. The medical provider is not able to pull up the light to examine the patient, so we really need to be able to detect without using light or trying to do a visible measurement of the volume the patient is losing. And then we also have examples of entry wounds where the fragments and the penetrating trauma travel extensively and the medic may not be aware of all of the internal trauma that's ongoing. So you can see on the top left picture here, this is showing you a thoracic MRI, but what you don't know here is the entry wound actually occurred in the neck, and the shrapnel had traveled the whole way down through the thoracic region and then exited through the abdomen. They couldn't find the entry wound for this, so what was happening was the medic was trying to pack the exit wound in the abdomen, never knowing that there was bleeding that was going on in the thoracic region. In addition to this, we're prepping for prolonged field care scenarios, and what this means is that we might have patients and service members in the field who have these slow but steady bleeds, and the medic may not be able to accurately determine their volume loss and be able to detect that the patient might go into hemorrhage over time, or hemorrhagic shock. So what else happens? Our service members are highly trained. They're athletes. They're trained to perform under extensive extenuating circumstances, including dehydration and high psychological stress states and things like that. So our service members can compensate. What that means is that we might not be able to detect changes in their vital signs until it's too late and they're already entering a state of hemorrhagic shock. So what we would like to do as a command on combat casualty care is provide our medics with the capability to detect shock before it happens so that we give our medics or our other medical providers time to intervene. In addition to this, another complicating factor is that physiological response to hemorrhage is highly individualized. I may lose the same amount of volume as anybody else here sitting in the audience, and I might go into shock 5 minutes before you, 10 minutes after you. It's highly variable. And just looking at a patient, we can't really determine when somebody is or is not going to go into shock and how much volume loss that they can actually withstand before that point. In addition to that, vital signs, the standard of care is just provider observation based on the vital signs that they have available to them at that time. There is no other technology that can detect when a person is going into hemorrhagic shock. So we would like to develop that technology to be able to give it to our medics and our medical providers. So what are we doing about this? So up at MRMC, we've developed an advanced medical monitoring hemorrhage detection integrated product team. So what does that mean exactly? So I'm from the science and technology realm, and what that means is that we're partnering with our advanced development colleagues to do some market research to figure out what is currently available to us to see if we can fill that capability gap of hemorrhage detection. So we did extensive market research, and what we realized is that there is no device out there that can do this. So what we're trying to do is to sponsor the development of a device or technology that can identify hemorrhage detection solutions for point of injury, roles 2 and 3, and then also very important to us is during transport. In addition, the technology must be non-invasive. We don't want to add any more invasive monitoring to our patients. So far, what we've done is we've leveraged the small business innovative research capabilities, and we've awarded a few actually grants related to hemorrhage detection. In addition to that, like I said, we've done extensive market research, and we've also sponsored multiple vendor days so that we can be aware of what's going on. Because as we know, technology advances at a very, very rapid state. So every other day there might be a new product out there that could help us address this capability gap. We're looking at multiple different types of technologies, including vital signs and hemodynamic monitoring, pulse oximetry, ultrasound and microwave sonography, near spectroscopy, as well as acoustic signaling. So today I'm going to talk to you about a device that's based on vital signs and pulse oximetry, and that device is called the Compensatory Reserve Index, and it's from a company called Flashback Technologies, which is out of Colorado. So what this is as you can see here on the middle of the screen, you have a standard pulse ox, which then has an added screen on it, and you can see on the right-hand side of that pulse oximetry in the center image, there is what looks like a gauge that goes, it's the white and red, and we like to call that our gas gauge. And what that's telling us is it's a value from 1 to 0, and that represents our CRI measurement, so our compensatory reserve index. And that trends with a patient's central hypovolemia, so it allows a medic to know, in theory, as the patient gets closer and closer to 0, that they're closer and closer to that point of deterioration and going into hemorrhagic shock. So what we're trying to do with that is give the medic more time to intervene. If they have to press fluids faster, if they have to push pressors faster, we're trying to stop them from going into that red and that point of decompensation due to hemorrhagic shock. So the CRI uses a machine learning and feature extraction algorithm. It's based on the PPG waveform, which is a standard data point that's obtained via the pulse oximeter. So it analyzes that arterial waveform. It has over 100 data points per waveform that it looks at. And it's designed to estimate, like I said, how close an individual is to decompensation. And we can see on the bottom left-hand side of your screen, this is just showing that because it is based on an algorithm, it can be embedded into other existing monitors. So any type of monitor that might have a pulse ox data endpoint could theoretically in the future also incorporate this machine learning algorithm and be displayed on other larger monitors as well. So here we can see that this is from a publication by the Flashback company from one of their preclinical studies. And this is just showing that the CRI measurement does in fact track with the patient's central hypovolemia. And you can see the progressive blood loss for the volume loss on the red line that goes the diagonal across the screen. And this corresponds to the green, amber red on the left-hand side of the screen, which is our typical gas gauge measurements as well. And then 0 represents the point of decompensation when the patient or the service member is going into shock. And then you can see as you continue to progress, if you don't have a medical intervention past that point, the patient will eventually go into hemorrhagic shock. So for now, the CRI has been examined in multiple animal models of hemorrhage, including large swine models. It's been used in the simulation of hemorrhage using lower body negative pressure in humans for their preclinical work. And then Flashback has also actually taken this device and this technology into the clinical field as well, and they've examined its use and its efficacy in pediatric burn patients and in adult trauma patients as well. And they've also looked at this technology not only within emergency departments and operating rooms and things like that, but they've also used it in transport, so ground ambulance and air ambulance as well. So in the future, what we're hoping to do is to bring this to the the operating environment so that we can detect hemorrhage. But in addition to that, it also has many other uses where it could be beneficial for us. Another example would be post-operative rebleeding. So a lot of that is internal, where the patient might be in the post-op room trying to recover, and a rebleed might occur, and this would also be able to detect that as well. In addition, we also see high value of this in mass casualty situations where a single medic is charged with treating multiple patients and might not be able to sit over and monitor that patient individually at all times. So I like to call this the set it and forget it technology, where you can put this type of monitor, the single pulse ox on the patient's finger, let them go if they're green. As they progress into the yellow and possibly the red, it lets the medic know, okay, I need to stop treating this person and go back to this person because they're in imminent danger and I need to do a medical intervention right now. And so in addition to that, we have mass casualties, we have point of injury, we have transport, and we have post-operative rebleed. So I think that if we can get this technology through the FDA, which we're working with the company right now to do, this is going to be extremely beneficial to the capability gap of hemorrhage detection for us. And that's all I have for you today, but if you have any questions, I'm happy to take them. Yes,
where the where the program stands
so just to repeat the question for everyone, and please correct me if I'm wrong, I was asked for an update on where the program is in the regulatory approval process. So the company CRI, Flashback Technologies, has a predicate device, which is tablet-based and it uses Bluetooth, that is actually already FDA approved, not for the indication of hemorrhage detection though. They're currently working for the miniaturized device, which I have at my booth over on the left-hand side, which is about this big. It's a ruggedized version. It's called the M1. They're working to put that through FDA approval right now, using their previously approved device as a predicate. The previously approved device, the tablet-based version, also uses Bluetooth technology, which we're not really interested in putting at point of injury. And the company has decided not to take that product to market since we are their primary customer, and that's something that we can't really use. So they're working to push the miniaturized, ruggedized version that has no Bluetooth capability to the FDA now.